Okay, so last time we had a look at curves in 2 dimensions, and we showed that, can you just shut the door, sorry, that it's always possible if your curve is parameterized by the distance, and we call that arc length parameterization, then the tangent vector is always a unit vector. And then the derivative of the tangent vector always points orthogonal to the tangent vector. And this is only true if the parameter is the arc length parameter S. Okay? And then also that the norm of the derivative of the tangent vector is basically your curvature. And what that means is that you can always fit a circle with 1 over the curvature to the curve at that point. Okay? And then I gave you the very practical means here of how I actually went and calculated everything. And you can go and try it on your own. In fact, you'll have an opportunity in the problem set to do one of these problems on your own. And so for some of this from you, it'll be review. But if you're not comfortable with this, it's going to come back again and again. Because I think all your projects at the moment have curves in them. And it's one thing to look at. And it comes in many other places. So what I'm going to do now is go on to 3D and see what else we have. So for the origami people, they call it space curves. I just call it curves in 3D. In GR, a lot of the things I'm going to say when we work in 4D also gets generalized. So yeah, it's sort of 2D is embedded in 3D and so forth. So curves in 3D are once again just a map from an interval to R3. And examples are the paper folding space curves, or basically any trajectory we have, like the planetary orbits or stuff like that. Okay, and the representation I'm going to use for the purposes of this talk is the parametric representation. There is another representation. What's another way of representing a curve in 3 dimensions? The intersection of 2 surfaces. So if in 3 dimensions I give you 2 functions of the coordinates, that is in effect specifying what a curve is. Okay, so for my purposes this thing works better, and this idea that you have the 2 representations comes back when we look at surfaces as well. So for others' purposes, the parametric representation, you have C, a 3-dimensional vector, and you simply write down its components as a function of the parameter lambda. And once again, you can go and you can define the curve, the length of the curve, simply as the integral over the interval of the norm of the derivative of the parameterized curve. Okay, so this is once again Pythagoras. And this is exactly the same as the 2-dimensional case. And then once again, you can go and you can say, I want to go to that preferred parameter, which I'm going to call S, so that if I increase S by 1, I've literally stepped a step of distance 1 along my curve. And so once again, you say, for all lambda in the interval, you define S of lambda to be the integral from 0 to lambda of the norm of the derivative of the vector pointing to each point on the curve. And so then the curve as a function of the parameter S has the same value as the curve as a function of the parameter lambda, which implicitly depends on S. And here this function that relates lambda and S is basically the inverse function of simply the distance of your curve. And even though it's sometimes hard to get this, you can still implicitly work with the arc length parameterization simply if you remember that DDS is related to dd lambda by multiplying by 1 over the norm of the curve at the point. Okay, so once again, S is in the interval from 0 to L, and this norm, dc ds is equals to 1. Okay, so it's literally making an arc length parameterization ensures that you always have a unit vector as a tangent vector. Okay, and then once we say that basically this parameter S traverses the image of the curve with unit speed. So very, very similar to what we did in 2 dimensions, except that we're going to get a little bit extra. Okay, so properties of 3D curves. What we have is you have your tangent vector that always points along the curve. So that's just derivative with respect to the arc length parameterization. If you have an arc length parameterization, then the tangent vector's norm is 1. And then you, just like in 2 dimensions, you define the curvature as the norm of the arc, the norm of the derivative of the tangent vector. So how big the change in tangent vector actually is. So if you have a straight line, what is the curvature?
Your radius is infinitely great, so your curvature is going to be 0.
Yeah, okay, because t doesn't change. Your tangent vector is just pointing along the line. And then if you have an arc length parameterization, your normal vector is equals to 1 over kappa s times dt ds. So once again, this normal vector, because kappa is simply the norm of how rapidly your tangent vector is changing, this thing is also a unit vector. But unlike the 2-dimensional case, where you only have need two vectors to span the space, and if you have your tangent vector and your normal vector, then you have 2 vectors that are orthogonal and you can span the space. You can't do that in 3 dimensions. We're still missing a vector. So a very natural way to construct another vector is simply to pick something. We know that t and n are orthogonal. Can you remember why? Okay, great. They are orthogonal because if you differentiate the fact that t dot t is 1, then you get d dt, something proportional to dt ds, dotted in with t, which is 0. And so as long as your curvature is not 0, then you have n dot t equals to 0. If your curvature is 0, that's also, you can't use the method, but it is also true. Okay. Okay, so now to span this 3 space, we need our third vector, which we just make by the cross product of the 2, and we call this b a binormal vector. So now, in this one sense, the first vector that points in the direction of the derivative of your tangent is your normal vector, and the vector that's normal to that one and the tangent is called the binormal vector. And these 3 vectors form what we call an orthonormal triad, okay? And in mathematics as well as in physics, we like them because it's easy to work with triads. They have some very, very nice properties. And intuitively, it's also very easy to understand what you mean when you express physics on them. In some sense, they are always unit 1, so whatever units you have is a direct relationship to distances. And so if I if I tell you not with all this background that T, N, and B are an orthonormal triad, what I mean is basically that they have these properties. They are orthogonal in that their dot product with all the others are always 90 degrees. And they are orthonormal because the norm of each individual vector is 1. Okay. And right, so that is a very, if you are given a curve, making this little triad is a very natural way of describing things around the curve. The only thing you have to remember is this thing varies at every single point of the curve. So as your curve twists around space, this triad goes with a curve. And at each point, it's completely stuck to the curve. So for example, you have this curve, right? What you then have is you have your tangent vector always pointing parallel to the curve, so the tangent vector is changing. You have your normal vector always pointing 90 degrees to the maximum curvature of the curve. So it's always going to point, so where it's strongly curved, it's always going to point into the circle it's curving around. And the third one is just going to be basically your right-hand rule that points up. Okay, so if you have your tangent vector, you have your normal vector, then your binormal vector is my thumb. Okay, so if you look at this curve over here, this part of the curve over there, say, your tangent vector points that way, your normal vector points towards me, and the binormal vector then points out towards the board. And as you go along, this thing changes, and I'll draw you a nicer picture, but that's what it does. It's literally stuck to your curve. So once you've defined your curve, you've defined that whole triad, and that travels along your curve. Yeah, it's like the tangent vector is always on the curve. The other one points in the direction where the curve is bending the most, and the third one is orthogonal to that. Okay, and I'll give you another very nice simulation that I spent hours making yesterday of what it's actually doing. Now, what you can do is just like we did in 2D, where I said there's a result if you have the curvature as a parameter, as an arc length, as a function of arc length parameter, then you can reconstruct that whole curve. Okay? A similar thing is possible here, but you need an extra function. Okay, so what you do is you can study how these vectors change along the curve. And the way that results in what we call Frenet-Serret formula. Okay, it literally tells you how these vectors are changing, and it tells you how they are changing based on themselves. So what this formula is, it's something that looks like this. Okay, and I've put it in matrix form because it tells you something else. It's basically a skew symmetric matrix where you have two functions, kappa and tau, both are functions of S, and it relates how your actual vectors are changing as you move along it to what the vectors are at the point of change. So if we look at the first component over here, we have T prime is equals to kappa times n. Okay, and that in fact comes directly from how we defined n, right? We defined n to be the unit normal of dt ds divided by kappa. Okay, so that first one is easy. Then we can go, and when we were given n, we defined the binormal vector, namely b of t cross s. Okay, and you can go about and you can work out its derivative, and you can work out the normal vector's derivative, and you can prove using these guys that they must be in this form. Okay, why?
I think something how I proved it initially, if you take the derivative of t dot t, you get 0. So, and that's how we proved they are 90 degrees to each other.
Okay, that's very good. So whenever you have a unit vector, in other words, t, okay, and all these are unit vectors by construction. N is a unit vector by construction. It is orthogonal to another unit vector, and so t cross n are also unit vectors. So b is also a unit vector. Whenever you have a unit vector, its derivative with respect to s is always normal to itself. Okay, so that means that along this, if you write down in general all these zeros, that basically translates you into having all these zeros, right? Because you can say, suppose t prime was arbitrary, I could always express it as a component along t, a component along n, and a component along b. This is basically what I'm doing here, okay? But it's not arbitrary. The fact that that t dot t is 1 tells me that t prime dot t is 0. and therefore, that 0 is there. The same thing is true for n prime dot n, means that 0 is there, and b prime dot b means that 0 is there. Okay? Then the reason this thing is 0 is because we defined n to actually be the derivative rescaled. Okay? So basically t prime is we define to be kappa times n, so that's why that thing is 0. Okay, so now what remains is we can say n prime, we know that the n prime dot n is 0, but these other two can basically be any functions. Okay, so we have any functions there, and what we also have is that b prime, we know b prime dot can be 0, but these other two can be any functions. And then what you must go and do is you go and you differentiate these properties, okay, with respect to proper time. And those properties will fix the fact that these arbitrary functions that you had here are related to each other, and that this one is related to kappa. So for example, if you go to t dot n and you differentiate it, okay, you get t prime dot n plus n prime dot t is equals to 0. And therefore, just by comparing that result, you're going to find that this thing is minus that one. So that's where that result comes from. And then similarly, when you go and you differentiate t prime or t dot b over here, and you multiply it out, you are going to get basically that this component is 0 and that component is arbitrary. And then when you evaluate n dot b, you differentiate it, you're going to find that these two are related. Okay, so these two functions that appear, the kappa and this tau, which I'm going to call the torsion, are, once you know them as a function of arc length parameter, you can actually reconstruct the curve, although the orientation might be different. But the intrinsic shape of the curve you will always get. And so what I want to do now is I just want to give you a feel for what this second parameter actually does. Most importantly, if the second parameter is 0, the torsion is 0, then you know your curve lies in a plane. Okay. And so just if we look at space curves, you have torsion in 3D. The torsion of the curve measures how sharply it is twisting out of the osculating plane. So the osculating plane is the plane where that circle that you can define with kappa actually lies. Okay, and another way of defining it also is it measures the speed of rotation of the binormal vector about a point. Okay, so it tells you how much the binormal vector is changing, but that you could have got from the previous description as well. Okay, so this is very, very useful because, for example, when we looked at planetary motion, I think we looked at, you guys looked at planetary motion last year. When you have your position vector r and the velocity vector of your planetary motion, right, you can basically go on and you can work out the torsion vector. And that's just the dot of, or the torsion, it's just the dot of r crossed the velocity vector. And you can prove using Newton's laws that that thing is 0. And then you can show that tau is 0 and therefore the orbit remains in a plane. Okay, so it's something you can literally do to a curve to determine whether it's 0 or not, or whether it's twisting out of the plane or not. All of Schwarzschild's orbits, both light and geodesics, you can show that the torsion is 0. They all remain in a plane. If you start in one plane, the orbit remains in a plane. So you can go about and actually check it, even though your coordinate system is very strange, right? So you can have their orbits in a very strange coordinate system. As long as if you work out the torsion, you'll find that it is 0. So let's look at an example. Okay, and so this example is basically a spiral, and the way I'm going to describe my spiral is I'm going to say, let me have a radius function as a function of parameters. So it took quite a lot of effort to get this thing to look nice. We said the radius is, say, simply 1 plus the parameter rescaled by 9. And then I'm going to define this red curve in terms of the parameter lambda. And this is not the arc length parameter. Okay, I'm going to define my curve as r cos theta, r sine theta, r cos lambda, r sine lambda, and then the height increases proportional to lambda. So we have our radius getting bigger, and we have our thing getting higher. And so we can see here where lambda equals to 0, we start at x equals to 1, and then r increases with lambda over 9, and the z component also increases with lambda over 3. So we end up spiraling around like that as we go up. Okay, so what do we want to do now? Well, we want to work out the tangent. So the tangent is easy. You just take this curve and you differentiate it with respect to lambda. So there we have dr d lambda is simply 1 over 9 times cos lambda minus r times basically plus the derivative of cos lambda, which is minus sine. And then over here we have sine of lambda times dr d lambda, which is basically 1 over 9, plus the r times the derivative of sine of lambda, which is r cos lambda, and here we have a third. Okay, so the tangent vector is pretty straightforward to compute, but once again be warned, this is not a unit vector. Okay, so we again go and we work out what the norm of this vector is. And you basically just dot this thing with itself, and you take the square root, and we get 10 over 81 plus r squared, where r is still this thing. And then what we do is we want to say, we want our new arc length parameterized vector, okay, which is basically our tangent vector made into a unit vector. Okay, and so this thing is a function of s, but these guys all are expressed as functions of lambda, which are implicit functions of s. So we can go about and we can differentiate this thing with respect to s by saying dds is just dd lambda times 1 over this, basically times d lambda ds. And so here we have it. So we have dt ds is equals to dd lambda of what we define t of s as, divided by this norm. And so we have an entirely valid expression for how the unit vector is changing, except that we can take our derivatives with respect to lambda, and we don't actually have to get the explicit distance parameter along the curve. And so I can go and I can do it. So I can say dt bar d lambda over here plus 1 over this thing squared over the norm squared. So there we have it. Minus basically t times dd lambda of 1 over t bars norm times 1 over t bars norm, and we get that. Okay. And then what we can do next is say work out the curvature, because the curvature is just now the magnitude of this thing, and I'm hiding things over here. These things are actually quite messy, and I actually am going to make you go through the pain of doing it this yourself, but know that this is the answer. So if you can derive this, you at least know what you're doing. Okay, so this is the curvature that we have, and what does this curvature refers to? It refers to the curvature of a circle, but the circle is no longer orientated in the plane, in the xy plane. It's orientated with an angle, and I'll illustrate it to you now just later when I sort of make a little simulation over here. So this curvature is basically related to the radius of an oscillating circle, but the oscillating circle's orientation points along this, basically this normal vector dTds. So let's have it here. For example, if we go back to our curve, right, here the curve is like this, your tangent vector points there, your normal vector points in the direction of the maximum curvature, and so you have a flat circle that is sitting along the normal vector like that, which is your oscillating circle. If you were to flip the curve like this, you would have your oscillating circle sitting in like that. Okay, and the B always is normal to the surface, your oscillating circle surface. Okay, and so what you're going to do in the rest of the exercise is find these B's and N's and tau's S explicitly. Okay, simply just by differentiating these things and using the definitions I've given you. But what I want to do now is actually, right. So first there's going to be this hint when you do it so that you can actually check that you have the right answer before you go on. And this problem is doable by hand. I can do it by hand, but you can also welcome to use mathematical mathics. Okay, and who of you know how to use Mathematica? No. Who of you know how to use, okay. I think I can make a little bit of demo. I've got it here, so that you can see if you at least want to learn it. Because it's very useful. I usually work the thing out still by hand firstly, and then I go and I check until I catch my mistakes using Mathematica or Mathics. But anyway, so I just want to illustrate here what is actually happening. So here what I did is I took a point on this helicoid. I literally went through the mathematics and I worked out what my dTds is, and therefore what kappa is, and what my normal vector is. And I construct my binormal vector from t cross n. And then you can also work out, if you have the binormal vector, you can work out what the torsion is as well. So what I want to illustrate here is at each point, my blue vector is my tangent vector. My normal vector points in from the tangent vector, and in that normal vector, in the plane created by the normal vector and the tangent vector, I went and I drew that circle with radius 1 over kappa s. So this little blue circle is my oscillating circle, and then B is the binormal vector. And you can see the oscillating circle fits it very well at the point, and then this red curve tends to curve up away from the oscillating circle. So the degree to which it curves up is actually measured by this tau of s. Okay, so, and you're also going to see I'm going to let it run a little bit, sort of up the curve. So as you move to the next point, your tangent vector remains tangent, your normal vector points in the direction of maximum curvature, and your B vector shifts. And how the B vector is shifting is parameterized by tau. So let's just go on. You can see the tangent vector remains tangent, the normal vector points in, the oscillating circle is the quadratic approximation over here at the point of contact, but it doesn't remain in the plane. The curve curves away in both directions, and the moment it curves away, your B vector is going to change. Okay, so there it changes. The curve, once again, is your oscillating curve, your normal vector, your tangent vector, and you can just see how it goes round. And you sort of have this wobbling circle that basically fits the curve very, very well at a point, and how its orientation is changing is entirely parameterized by your torsion. Okay, so we can run it backwards. How cool is that? Okay, so your torsion and your curvature are the minimum you need to describe a curve in 3 dimensions. Okay, another thing, these oscillating circles are very, very good. Are very, very good approximation of the circle at a particular point. Right, it's like the second order approximation. And a lot of mathematical methods are actually designed using oscillating circles. When we do perturbation theory of planetary orbits, you tend to approximate it with a circle like that, and then you work out how circles change. People have tried to do it in GR but not succeeded to the same extent. It's something I still also want to do, is the orbits you are working with are geodesics. When the little body that's orbiting around the big black hole is not a point mass, then the orbits depart from geodesics. And what you then try and do is you fit the oscillating geodesics, the best possible geodesics at the point. That's a really, really hard problem, but it's something I'm interested in. So this idea of making a very good approximation locally of your curve with some thing you know and understand that's related to the properties of the curve, this is the simplest example, but it's a profound one. It's been used very many times in physics and finding sort of high order perturbation techniques. Right, so that concludes our introduction to curves in 3 dimensions. Have you seen this before, the torsion thing? No.
But it's very cool.
Okay. It's very powerful. So you're going to have an opportunity in the problem set to play with it. The hints are there. And I'll show you actually, maybe I'll show it to you just now before I go onto the surface, how I actually calculated this thing. Okay, sort of got these things. I did it by hand because I know how the sine and cos combine, but then I actually went and checked it because I plotted it in, I actually plotted in LaTeX, and LaTeX is not that good at plotting. Sometimes there are mistakes in there that are not due to mistakes in your formula. So I didn't get what I wanted exactly the first time, and then I went and checked it in MathX. So let's see if I have it. So MathX is an open source knockoff of Mathematica. You can get Mathematica on campus, okay, but then you have to be connected to the campus server. So it is freely available, so you should actually go to the software website and try and install it on your computer because you can use it whenever you're on campus. Mathematica is stronger than MathX. Okay, it's just that MathX is free and I can use it at home. Okay, the notation in both Mathematica and MathX are exactly the same. Okay, so that's the reason why it's a nice illustration. So in fact, MathX, this version of MathX is still like the way Mathematica started. It's like the pre-version. It's not got the fancy GUI. And the reason I do that is it simply uses less memory on my computer if I run it this way. Okay, so Mathematica, if you actually get it from the campus or run it on one of the campus computers, or for the purposes of the stuff we're doing, it's so lightweight you can actually just run it on a web. There's a web app on Mathematica as well that you can use. So then you don't even have to download it, and then you can get it at home as well. Okay, the way Mathematica works, it's slightly different from Python or MATLAB in the sense that it's a symbolic language. And so this is actually what I use to compute that curve. And so what you do is you make a number of definitions. I actually wrote the stuff. So I'm just going to run the, I have all the commands I wrote. So I'm just going to run it to show you how I systematically went about doing it. So what I did is I basically said, I defined it that r of x, remember my radius, okay? If you make a definition, you say it's r is a function of x, and x is a variable, so you put an underscore underneath it, is equal to, and this is a definition if you have the double dots, equals to 1 over x over there. And so if in the big Mathematica, what you're going to have to push is Shift-Enter to run something. Here you just have to push Enter. So you enter it and you've got no output because that's just a definition. So that's how I defined R. Then I went and I defined my curve. Okay, so there we go. I defined my curve. It's just basically R of x times cos of x. The reserved functions in mathematics are capitalized, most of them. Comma R of x times sine of x, comma x over 3. So that was my curve. So then shift enter, and there it's not a function definition, it's just something that I kept. And so whenever I type in CUR, I'm going to get this expression out. Okay, then so that's my curve. Then I wanted to go and work out the tangent vector, and then I wanted to go and work out that norm of t. Okay, so the tangent vector is just the derivative of curve with respect to x. So there you have d curve comma x dotted in with d curve comma x simplified. So that's our norm squared. Okay, so you just do that, and there it actually works it out. Okay, so that's our norm t, and then I went and defined my unit vector. Where's unit t? No. Yeah, then I went and defined my unit vector t as d, the curvature, divided by the square root of its norm. Okay? And there it gets a bit messy, but this is basically my unit vector t. And then I could go about working out the derivative of the unit vector t by simply simplifying, basically taking the derivative with respect to s, so that's the derivative with respect to x, divided by that d lambda. And there I basically worked it out. And what simplify does, it doesn't work perfectly for mathematics. It basically tries and combines things in a way that's very simple. Okay, and this is still not simple. What I typically do when I get expressions like this that's hard to read is I ask it for the coefficient of everything in front of sine. Okay, and then I simplify that, and then I write it down in wherever my notebook is, and then I ask it for the coefficient in front of cos. I simplify that separately, and then I write that down. So what this thing is not good at is knowing how you actually want to simplify it. So the way I ask it for the coefficient is there we go. I say I want the coefficient of this d unit vector in front of cos. Okay, and once I've got the coefficient, I actually don't want to get it in terms of lambda. I want to have r as the variable, and then I tell it to simplify it, and once it's simplified it, it must factor it out. Okay, and that's what I then get. For each component, I get whatever was in front of cos simplified, and you can go back and you can check that derivative of the unit tangent vector was found there. And then I basically did the same thing for sine, and then I got the coefficient in front of sine, and then what I did is I set both sine and cos to 0 in here, and then I got whatever remained. Okay, so that's if you put both the sine and the cos in that unit vector to 0, then you just get the last term, and then you can simplify that as well. And that's sort of the way I go about working out that dTds, and it's the same way, you're just using the definitions that you can go about working out the others. Almost all the exercises in this course you can do by hand if you take long enough. In fact, most of them I've done by hand, but if you want to check, learning how to use one of these computer algebra things is a good idea, and it'll save you a lot of time in other things as well. Mathematica, as I said, is easier to function than this thing. In fact, Mathematica is a lot of help. In fact, when you start typing functions like cos, it starts giving you the options underneath. So it's very quick to learn and very, very easy. As I said, the only problem is the licenses are stuck to campus. But it's well worthwhile to just go and poke around there. I think you'll actually save yourself a lot of time. It's very similar to MATLAB's, that symbolic stuff that you were using in MATLAB. I think you recognize some of it from there. Okay. Right, so that is just a calculational thing. Let's go back to just the introduction to surfaces. Okay, so we've done with curves, we've done some little bit of calculation stuff. Let's start looking at surfaces in 3 dimensions. So once again, in 3 dimensions, there are different ways to represent a surface. Okay, and the reason I'm saying this is because this actually becomes important when we start doing manifolds. Okay, so the one way, and this should just be a reminder, the one way you represent a surface is basically implicitly in 3D. You go about and you say, I have a function of x, y, and z, and it's equals to 0. And this way of describing is you simply describe one scalar function. Okay? And then what you go is you can work out the gradient of the scalar function, which is just the gradient of f, which is a vector, which then gives you something that is normal to the way the surface is changing. Okay. And then you can work, then you have the second thing of the tangent space. And the only thing you know of the tangent space from this definition is that it is spanned by 2 vectors, right? Because you have a surface, you always have its dimensionality 2. It's spanned by 2 vectors, and I'm going to call them TA and TB. And what you get from this definition is that they are both orthogonal to the gradient. So you have the property that TA dot the gradient of f is 0 and TB dot the gradient of f is 0. Okay? But you don't necessarily know what TA and TB are. And so what you can do is you can pick any TA that has this property, okay, and basically solving this equation, and then pick another TB that also has this property, and then make sure that the 2 are 90 degrees each other. So Gauss-Georgian orthogonalize those 2 vectors. So it doesn't give you a direct prescription of getting tangent vectors themselves. The only property it gives you is that it's got to be normal to your surface. And so, for example, in the unit sphere, we basically have a function, and this function is not unique that describes the surface. We can have the function that x squared plus y squared plus z squared minus 1 times some other constant must be equals to f, and therefore f equals to 0 describes the surface of a unit sphere. Okay, and then you can go about and you can say the gradient of f is just x, y, and z, okay, because it's just the derivative of this thing, which is just r times the normal vector. But because you've restricted r to be 1, you effectively have that it's just a normal vector er. Okay, so here you have the surface described implicitly. Here you have the gradient, which is just er. And you can now go about and choose any 2 vectors to span the tangent space, provided they are normal to er. And typically the ones we use are these 2. Okay, but I haven't told you how to get these 2. At the moment, the tangent space is just anything that's normal to this er. Okay, So that's the one method. That's a totally fine method. It has a lot of benefits. When we simulate general relativity spacetimes, we basically say we have several of these surfaces and they all connected. We call it a foliation, like a book. We basically chop our spacetime into various little leaves like that, and each of those surfaces are identified by a function equals to 0 or equals to a constant. Okay. Another way to parameterize surface, and this is the way that we're going to use when we do look at the origami surface, is basically to explicitly give each point on the surface as a function of two parameters. And that's what we call the parameterized sort of description of the surface. So there we basically specify a vector that points to each point on the surface, and that vector is parameterized by two parameters. So we basically have a description that takes two parameters, u and v, to R3. Okay, and that description, if we're doing it for the unit sphere, it's basically the surface is parameterized by theta and phi, and then every single point in 3 space on the surface is described by these coordinates. So the x coordinate over here is basically sine theta, so it is that guy times cos phi, so there's the x coordinate. The y coordinate is sine theta times sine phi, so that's that coordinate, and the z coordinate is simply cos of theta. So you can see this way, whenever you for any value of theta and phi, you're on the surface, and any point on the surface has a unique theta and phi that actually gives the description, and that we call the parametric representation of the unit sphere.
Say this was no longer a unit sphere, but let's say a sphere of radius 2, will then there be a 2 in front of each of these?
Yes, because you have to specify points on the surface with this description. Yeah. So that will be exactly what it is.
Okay, so for anything else, we would have to add a radius in front of it to indicate how far it's from the origin.
Yeah. In fact, you can view this thing as being you can view all of space. You can view a foliation of 3 space to be made with a whole bunch of spheres that are like nested inside, like one of those Russian babushka dolls. You know how they nested inside? So you can view all of space to be a foliation like several spheres like stacked around each other. And that's basically what and then the way you identify the sphere is the radial coordinate. Okay. Similarly, you could basically foliate all of space with those funny little dolls that you pack inside of each other. And then you could say, the size of the doll will tell you which is your doll coordinate, and then where you are on the doll will be your theta and phi coordinates over there. Right. So now the partial derivatives of S give us vectors of spanning the tangent space for this description. So this one is convenient. This one is convenient because you immediately know what the normal is. This one is convenient because from the description you immediately get what the tangent space is. So if you look at this, and we can just do the partial derivative with respect to phi, okay, and theta. So the partial derivative with respect to phi is sine theta in front of both times e phi, right? E phi is basically this vector that points at 90 degrees to that radial or that radius. So that vector is then minus sine phi cos phi. E phi is minus sine phi cos phi. So the partial derivatives of S are proportional to unit vectors in the tangent space. And similarly, ds d theta, okay, is how theta is changing. And here you can see if you take this derivative, instead of pointing out that way, it points directly down. Okay, and this vector is exactly the derivative of S with respect to theta. Okay, so the different descriptions have different benefits. Once you've gotten the two tangent vectors for S, you can normalize them, and then you can work out the normal vector, to the tangent space by taking the cross product of these two. Okay, just like we did with the curve. Two vectors you can always work out, and then you can basically prove that that normal vector is proportional to the gradient of various of these surfaces. Okay, important when you are taking derivatives like this. In this example, these partial derivatives were orthogonal. Okay, that's not necessarily the case. You can get a parameterization of the circle where if you take the partial derivatives, they are not orthogonal, but they will always be in the tangent space. In other words, you can have a parameterization where if you take the partial derivatives, you get two vectors, but their angle is not 90 degrees. Okay. Another thing is some of this stuff, but not all of this stuff, generalizes to all manifolds, which is why the last time I was careful not to introduce it this way. Okay, so that's just a caveat. This gives you a very good intuitive feel, but when I'm going to do the manifolds, I'm going to build everything up from scratch. And then there are subtleties that come out that this example will confuse you with a little bit. Okay, so this, put it in the box of things embedded into 3 space for now. Okay, and then when I'll tell you where it starts departing. But just when you play in 3 space, and we play with it a lot, this is basically the 2 representations you have. So I think somebody's got to teach now. Right, I'm actually going to stop the lecture, and then I'm going to continue the next time and probably get you like a problem set of the first couple of things. So next time we basically have all the basics we need about curves and surfaces, and we're going to start looking at deriving the conditions for the origami folds. And then after that we're going to go for the full general bash at building up the geometry structures from basically set theory. So questions? Happy? You're learning things that you want to know? You're scared of what you're learning?
Yeah.